TransOps Fluid Flow Piping Project by Samuel Bynum, Tara Schumann, and Fahad Alanezi at New Mexico State University Chemical Engineering Department, class taught by Reza Foudazi. Now, for our project, we're told a pump delivers a steady flow of water from a large tank to a house. During the pipeline, the flow is split to 4 different destinations: the garden, bathroom, kitchen, and a warehouse. The total length of the pipe network is 60 meters. We are asked to find and use appropriate pipe fittings and a pump to build this water distribution system with minimum cost and pump head. So where does one begin? Well, we started by selecting a pipe type and a pipe diameter, finding relative roughness, solving for velocities in our pipes, determining Reynolds numbers of our pipes, solving for friction factors, adding up minor losses, determining head loss, finding pump head required, and solving for mechanical power that must be added to your fluid. Now, as you move away from your pump, your pipes will begin to experience pressure losses due to frictional forces between the fluid and the pipe, bends in your pipe, as well as viscous forces of your fluid. Now, we took our piping sections and broke them up into several different sections, which we first calculated head loss after our pump. We then calculated head loss in the garden, next head loss between our garden and bathroom, head loss in our bathroom, head loss between our bathroom and kitchen, head loss in the kitchen, and lastly, head loss to our warehouse. Now, once you calculate the head loss in each of these components, you can then add them all together to calculate the total head loss of your system. Once you have the total head loss in your system, you can then plug it into your energy equation to calculate your total useful head. Now, the energy equation reduces to the useful head set equal to the difference in elevation of open reservoirs plus total head loss. Our useful pump head came out to about 15.44 meters. After we calculated useful pump head, we could then calculate the mechanical power required by our pump. Now, most pumps have an efficiency between 50 and 85%. To be conservative, we estimated with a 60% efficiency, which brought our pump power requirement to 10,350 watts or 13.9 horsepower. Once you calculate the mechanical power for your pump, you can begin to shop for pumps. Now, shopping for materials was the worst part of our project, as you can see, because our total came out to $16,823.01, with the bulk of our money being spent on galvanized steel pipe, brass pipe, and PEX pipe coils. However, we believe that the hallmark of engineering is creating products that will stand the test of time, as opposed to using cheap alternatives that will leave you spending more money in the long run due to constant maintenance fees and repairs. Here's a list of our references that we used in calculating all these, most of them from our fluid mechanics books, and the links to our materials bought can be seen in our actual written report.